borane molecules. But old school people usually just write that you have just pure borane. They won't even tell you what the solvent is, all right? And so after that, what do we have to follow up with? Hydrogen peroxide and sodium hydroxide. And of course that is all dissolved. Note that the hydrogen peroxide is necessary there, and it's the only peroxide that you can use. Looking at it show that out, and the hydrogen peroxide is necessary to insert itself into the carbon boron bond that's broken off by the hydroxide, so you can't use like benzoic peroxide, so it has to be hydrogen peroxide. Like that. Let's take a side trip real quick about that hydroboration oxidation. Let's say that we have that stuff, and I want to make that stuff. What reagents can I use? That becomes a long route. It's a hydroboration mechanism again, except in this case you use a bulky borating agent, followed by the same, that hydrogen peroxide, sodium hydroxide, and water. Note that the intermediate here, it's fleeting. It doesn't stick along for very long, but the intermediate is this stuff. What is that stuff? What do we call that? There's a word. It's got an alkene on an alcohol. An ene and an ol. An enol. What do enols spontaneously do? Excellent. That's going to tautomerize. There's no way to stop that. We can't capture that stuff. This is fleeting. It exists for a few moments and times before it'll spontaneously tautomerize into the aldehyde. All right? And then another thing to note is that R2BH. It's tempting just to memorize this or to memorize one example, but you kind of want to understand, what do those R groups have to be? They have to be something. What do they need to be? They have to be bulky. So some possible examples of that would be like a tert-butyl. You could have I think one example they use in the ACS book is a cyclohexyl group. All right, if you saw those on the exam, would they freak you out? Well, they probably would have 5 minutes ago. Will they freak you out now? No, we're all gonna know those stand for R2BH. Yeah, and that can be a variety of alkyl groups, right? Tert-butyl group, cyclohexyl. I think there's one that is I can do this. It's like I think that stuff is 9-BBN. It's like this bicyclic compound that's got those really bulky R groups hanging out there. Are we all good with that?
So the R group doesn't matter what it is.
It just has to be an alkyl group. Yeah, it just has to be an alkyl group. It doesn't have to be anything interesting, and then people who actually do this for a living will change that R group to get the best result. So like the tert-butyl might work better on a certain aldehyde than another. One might be cheaper than the other. So in the real world, people choose for a number of reasons. But but on your test, just be prepared for any possible right. Just know it has to be some bulky alkyl group. Are we all good with that? All right. Am I working, Justin? Okay. All right. Are we all happy with this? Cool. All right, this is a common theme that comes up on the ACS. It'll be like possibly 1 or 2 questions, and it usually weirds everybody out because they've never seen that before. But just note that that R2BH is going to be some bulky alkyl group, and the ACS usually writes it as the actual alkyl group. Yes. For the alkene, that thing has enough of its own steric hindrance that the regular old boron will work perfectly fine. For the alkyne, it's not quite sterically hindered enough in the alkyne where you need to make the borane also bulky. So hypothetically, you could use this on an alkene, but I think these things are kind of expensive, so that might not be the best idea. Good? Do we have any questions on this? Good? All right. All right, so our next question says, make propanal from butene. That's kind of hard to read. Oh. All right, make propanal from butane. So let's draw that. So we are wanting to take butane and make it into propanal. Good? So it looks like we lost a carbon there. I'm thinking we're going to do a similar setup that we did for the first one, where we're going to introduce functionality using either bromine and light or MBS and heat, and we're going to get this stuff. Cool? We want to remove that functionality, and I'm thinking we're probably going to make that terminal. What sort of base do I use to make it a terminal alkene? Bulky, so we want something like terp butoxide, and that's usually run. And also be aware, if you guys do an elimination with some base is almost always done in the solvent that is the alcohol of that base. So like if you use terp butoxide, terp butanol is the solvent. If you use sodium methoxide, methanol would be the solvent. If you use ethoxide, ethanol would be the solvent. Are we all good with that? So if you see that alcohol there in addition to the base, just know that it's a solvent. Are we all good with that? Yes? Right. From here, if I want to cleave off a carbon and make an alkene, what reagents can I use? Or an aldehyde, I'm sorry. Make an alkene into an aldehyde. That would, I don't know what that would do to an alkene. We're losing a carbon, we're doing a cleavage here. Say that again. Excellent, we can use ozone. And what does DMS stand for? Dimethyl sulfide, so it's a sulfur group with 2 methyls attached to it. Or what else could we use here? Anybody remember anything from Organic 1? No? We can use some sort of metal and H3O+. So we can use what we'll do is they'll take some sort of metal, usually it's like ground up in a powder, and they'll dissolve it in acid, and that'll be essentially an electron source. Those metals can include zinc, iron, nickel, really, they're a variety. If I remember right, zinc and iron are the common ones. If you're in a pinch, you could probably use some other metal, but just be prepared to see iron or zinc. Those are the most common ones. Cool. And then note that dimethyl sulfide, DMS, will often be written as SCH32. Good. All right. A good rule of thumb is that if you only know the acronym, you're probably not going to be able to answer that question on the ACS. All right. They don't very often use acronyms. They almost always use either words or structures. So, as you guys are reviewing, just make sure if you use any acronyms, make sure you know what they mean. CH32, yeah. And then remember, MBS is N. Excellent. I can never cinnamide. I think I spelled that right. But it's going to be a nitrogen locked up in a ring with 2 carbonyls, and then it's bound to a bromine. Good. Any questions on any of that? No? For this, yeah, for this one, this will cleave off that guy, and it will produce that guy, and I think one of the byproducts would be formaldehyde. But we're not, that stuff will evaporate fairly quickly, so we're not too worried about that. If they're major or important side products, yes. But if it's something like that, usually not. Usually if you can identify the key product, you should be able to narrow it down to at least two, and the other answers there should be something in the answers that doesn't make sense. Good? All right. Let's move on to our next one. We'll actually get rid of that. All right. Let's detour for a minute and talk about mechanisms, just because those tend to be something the ACS talks about, but in kind of a weird way. So the way they'll ask these, they'll ask you to identify a key mechanistic step, ask you which of the following is a reasonable intermediate. They might ask you which of the following is the most stable, either a radical, an anion, or a cation. If you don't know mechanisms, this will be rather difficult, so just be aware of that. The two that I really want to emphasize, though, is first, let's talk about the dehydration of alcohols, and then we'll talk about electrophilic aromatic. So I'm going to kind of denote this away at first and just call it H+. And we're going to say it's a dry acid. What is the most common dry acid that's used in organic chemistry? Sulfuric acid. Do we know any other dry acids? That's very wet. Phosphoric acid's a good one. So H2SO4 and H3PO4. So we have some dry acids. Some examples of that are H2SO4, H3PO4. This one is often ignored, but it's a derivative of sulfuric acid. It's actually that tosylate. It looks like, yeah, it's some, I don't know what its actual name is, but that structure is the tosylate, which is why it functions as such a good leaving group, is because when it leaves, it is the conjugate base of an exceptionally strong acid. Are we all good with that? And this stuff can also be denoted as TSOH. Cool. But those are all dry acids. Those will all function in the method. If anybody takes the organic lab, you guys actually do a reaction similar to this, where you'll make a mixture of phosphoric and sulfuric acid, and you'll use that to dehydrate an alcohol. And then remember, the first step of this guy is a proton transfer. So what we end up getting is this water molecule, which is a good leaving group. What happens next? Excellent. Water will leave. Now, is this carbocation stable? It could be more stable. What has to happen for it to be more stable? Excellent. So we'll actually have a hydride shift, and what we'll end up getting is that guy. Cool? Now, the product, whether you had considered that the first carbocation as your starting, or that second one as your next step, you'll get the same answer. But ACS doesn't often just ask you to like predict the product. They'll ask you for a key intermediates in the mechanism. And note that this is an important intermediate, because this allows us to show why H2O can grab either that proton, or it can grab a proton from one of the methyls. And so in your reaction vessel, what you'll get as a mixture of products will be that guy, and you're actually can potentially get a little bit of that stuff. All right. Now this guy That's going to be your major product. But these two are possible, right? They're not going to be in very high yield. If you let that stuff boil up long enough, you're likely to get almost entirely the more substituted alkene, but it is possible to get some of the other two due to that first carbocation and that second carbocation having a proton abstracted. Are we all good with that? Do we have any questions on that? Good. All right, so just keep in mind that when you guys dehydrate an alcohol, carbocation rearrangement is very frequent. So when people actually do this in real life, they try to avoid using things that are going to rearrange. One thing to keep in mind about the rate of this, which one is more stable, a tertiary carbocation or a secondary carbocation? Tertiary. So which one is going to proceed with the fastest rate? An alcohol that forms a tertiary carbocation or an alcohol that will only form a secondary carbocation? So that first step's rate determining. Everything after that we don't care about. We only care about the rate determining step. So carbocation formation is rate determining. So which one's going to react faster? Tertiary. And in fact, if you take those three and you reacted each of them individually with sulfuric acid or phosphoric acid and you did a dehydration, which one's going to react the fastest? Tertiary. Which one's going to react the slowest? Excellent. Yeah. If is anybody here in the forensics program or the chem program? Yes. When you guys, so one of you will take the second organic lab, and they actually do an experiment similar to this, where you take a primary, a secondary, and a tertiary alcohol, and you react it with a mixture of acid and halogens. So you'll take like sodium bromide and sulfuric acid and mix it together. That last one, that takes about an hour and a half to react. The first one, that tertiary alcohol, only takes about 5 minutes. So you see that difference in rate there, how that third one, because it's primary and it needs a primary carbocation to form or to do a concerted mechanism, that's going to take significantly longer than the tertiary alcohol, which only takes like 5-10 minutes, and you just have to shake it up. Are we all good with that? Yes? So we could answer questions about rate on the ACS. Cool? All right. Next, let's talk about electrophilic aromatic substitution. Well, actually, we're going to talk about two of these. So we'll call this, let's just call this group X for now. Right. Let's first start by saying if we have some compound with a electron donating group, and we'll use a lone pair, it's just an electron donating group, and we react it with some electrophile E+, we're going to have two possible attacks. We're going to either go for the ortho position or the para position. We'll draw this one as para, so that guy attacks, and what we get as a result, whoops, no, I don't want it in there, like that, is we get that stuff. Now that stuff has a number of resonance forms, and on the exam you want to either be able to sketch them out very quickly or be able to identify them from just looking at them. What sort of charge does this guy have on it? Positive. So if you saw an answer choice that had a negative, would you mark that as correct? Totally. You say that, and I kind of believe you. Note that this guy on the end and the first one are both important, all right? You can't just draw one. All right, showing that positive charge delocalized across multiple carbons is what makes the sigma complex more stable than, say, just some primary carbocation. We all good with that? Yes. Um, so what the ACS will do is they'll give you that starting material. They'll give you some electrophile. They'll usually give like bromine or nitration or something, and they'll say which of the following is a reasonable key. Which of the following is a reasonable structure for the key intermediate? So we want to be able to look. Yeah, any of those guys. All right. For the addition of some electrophile to a bromobenzene or anything with oxygen or nitrogen, note that the important one is this guy. Why is this one important? If this were a methyl group here, would this structure be here? No. So if we have a lone pair on our electron donating group, we're going to get this additional resonance form. Which one is better equipped to handle a positive charge, carbon or oxygen? Oxygen. Carbon or nitrogen? Nitrogen. Excellent. What about carbon or a halogen? The halogens, all right? All of those heteroatoms are better equipped to handle that positive charge, which is why in the case of phenol and aniline and anazole and all of those guys, they'll react significantly quicker than benzene. The halogens are the bad actor there. They have some inductive effects that have to be taken into account. There's poor orbital overlap and stuff, but for the cases of phenol, aniline, anazole, N-methyl-aniline or N-dimethyl-aniline, those will all react significantly quicker because of that structure, all right? This structure is also why bromobenzene and chlorobenzene are orthoparadirectors, even though they have a slower, even though they're deactivating in the inductive sense. Good? The next one we want to talk about is, remember that this set of structures will not be the same if we have a meta director on here. Like let's say we have some like a nitro group, all right, and this is an electron withdrawing group. All right, these guys can be nitro, the sulfonic acid. It can be a trifluoromethyl. All right, any of those guys are a carbonyl. Anything that's a strong electron withdrawing group. If we react that with E+, what we're going to end up getting is a sigma complex with the electrophile meta to the substituent on the ring. All right, and that's done to prevent placing the carbocation on the carbon bearing the nitro. Because if that were to happen, what we would have is two positives right next to each other. Nature doesn't like charge buildup like that. It prefers to either have a negative and a positive or to just not have charges at all. Are we all good with that? And again, you want to be able to recognize these guys on the exam. Good. My suggestion would be practice sketching these a few times. So think of it with some generic electron donating group, think of it with some generic electron withdrawing group, and then be able to recognize examples. And remember that typically an electron donating group will have a lone pair on it, or it'll be an alkyl group. An electron withdrawing group typically has a double bond that's conjugated with the ring. So in the case of carbonyls, in the case of a nitro, a trifluoro group doesn't have a double bond, but it does have those fluorines that are all highly inductive and draining electron density out of the ring. Good? Questions? All right. One more that we want to talk about. So this is actually kind of interesting experimentally. What someone tried way back in the day was they took chlorobenzene and they reacted it with sodium hydroxide, and at room temperature, what happened? You react chlorobenzene or bromobenzene with sodium hydroxide at room temperature, what happens? This is allegedly something you learned in the last few months. That's what we're hoping happens, but does that actually happen? No, there's no reaction here. This stuff No reaction happens. Now, the people who were studying this, they were kind of stubborn, and so what they did was they're like, well, if we heat it up, it'll go. It's not the best logic, but it ended up getting them the answer. They found that if they heated it up to, I think it was like 300 degrees Celsius and like super high pressure, you would get this stuff. Okay. How did that happen? Did this go via a substitution like an SN2, SN1 that we learned in Organic 1? No, remember that sp2 hybridized carbon's kind of finicky. It's not going to easily lose that chlorine to produce a carbocation, and it also, we can't do a backside attack. If you think about that, a backside attack would require that OH getting into the ring, hitting that and causing that ring to flip inside out. If you can envision that happening, probably want to reconsider taking this class again, because that can't happen. Are we all good with that? No substitution on benzene rings in terms of SN1, SN2. Does anybody remember what the intermediate was called in this mechanism? Benzyne. It's kind of weird. We learned in Organic 1 that we have to have a linear setup for a triple bond to form. And what actually happens is that hydroxide grabs a hydrogen, that hydrogen lays down and kicks off that chlorine, and we get this thing that's kind of weird. It's got a triple bond-like structure there. Cool? Benzyne. Yeah, benzyne. Whether it's an actual triple bond or a very, very weird diradical, there's still like debate over what it actually is. But this stuff only forms at extremely high temperatures and pressure. There's a huge activation barrier there. From here, this stuff will react with more hydroxide, and after a number of steps, what we end up getting is the OH. Good? The key here, and what the ACS often tests on, is the order of steps, all right? The first one is an elimination. Good? The second one is an addition. Whoops, I wanted that in red. Are we all good with that? So benzyne is elimination, then addition, all right? There is another mechanism, and we're going to draw that out here in a second, that is an addition, then an elimination, the Meisenheimer complex, all right? You want to be able to recognize the difference between the two, because the way the questions are often worded is such that they'll say, what's the order of steps here, all right? And if it's something where there is no electron withdrawing group, there's just a chlorine, or it's like a chlorine and a methyl, you will get a number of products. A side note as well, what they also found out with benzyne is that you'll get a mixture. Either one of those carbons can have the hydroxide added to it, all right? So just be aware of that. Are we all?
Would that be the same thing?
In this case, yes, but what if I put a methyl here? Yeah, so just be aware. If there is a methyl hanging out there, and they'll often do that, they'll put a methyl there and say, what products can result? If it goes via benzyne, you will get a mixture of hydroxide being added to either one of those carbons. And I think the relative ratio is close to 50%. There's no real favoring of one over the other. Good? Yes? All right. Let's talk about the next guy, which is the Meisenheimer complex. So what someone else found out was that if you take, and let's actually walk through the synthesis of this stuff, is if you take benzene, you can chlorinate it, and then you can nitrate it, and we'll get a mixture of ortho and para. For now, we'll assume that we can separate those. You can nitrate it, and then you can actually react this stuff with sodium hydroxide in like about 100 degrees Celsius. That's not that hot. You can just boil water up and put it in that steam bath, and that'll be about 100 degrees Celsius. All right, this isn't anything extreme. And you can get Yeah. You get that stuff. Are we all good with that? Right? If I want to add a chlorine, what reagents would I use? Blah, blah, blah. Cl2 and yeah, I want some sort of catalyst. That will come often in the variety of either aluminum trichloride, or you could potentially use iron trichloride. I think the one that most people use is the aluminum one, but just note that some sort of metal catalyst, either aluminum or iron, is necessary, and that's that Lewis acid catalyst. Good? If I want to nitrate, what reagents do I use? Excellent. We'll use HNO3, nitric acid, and H2SO4. And both of these mechanisms, both the chlorination and the nitration, go via the electrophilic aromatic substitution, where electrophile is formed, the ring attacks an electrophile, has that sigma complex, and in the case of the chlorine one, you will have multiple resonance forms due to the chlorine donating its lone pair. Good? All right. Now, this one doesn't go via the electrophilic aromatic. What do we call this guy? It's nucleophilic aromatic substitution. This has that Meisenheimer complex. So what happens here is that we have this chlorine, we have this nitro group. What happens first in the mechanism? Say that again. Excellent. So in the first step, that hydroxide attacks there. It forms a lone pair, and we're going to talk more about this intermediate in a second. But we essentially have a negatively charged intermediate, and then the next step we lose chlorine. To produce paranitrophenol. And in this case, we do not get a mixture of products where we have like para and meta, because we're not forming an intermediate that can react at either site. All right? And then for this, what happens first, addition or elimination? Addition, and then we eliminate. All right? And I just want to emphasize the difference between those two. So note that in this guy, we had the elimination and then the addition for benzyne. In the nucleophilic aromatic substitution, we add the hydroxide and then eliminate it. Does it have to be hydroxide here? No. In fact, you can use sodium amide, you can use sodium methoxide, sodium ethoxide, and you can make aniline, anazole, and ethoxybenzene derivatives. All right? It just has to be some sort of nucleophile that's reacting there. All right, so let's highlight that. So for this, we can replace this guy with sodium amide. We can replace it with sodium methoxide. We can replace it with potassium. That's sodium ethoxide or potassium methoxide. All right. The counter ion is not so important. It's more so the fact that we can have the N minus, the OET, or the OCH3. Good. And those will all do the same thing, same resonance form, just a different substituent being added. We all good with that? All right. Let's talk about that complex real quick. Note that this guy is similar-ish to the sigma complex, but there's a few key differences. What's the charge on that guy? Negative, and that negative is important here. All right, it's an easy way to eliminate answer choices on your test, because if we know that it's going via a nucleophilic aromatic substitution, what we know is that it should have a negatively charged intermediate. Whoops, I probably shouldn't have switched those, but whatever. And you guys should ideally be able to draw these as fast as I'm drawing them right now. Cool. And sorry, I shouldn't have switched those two, but it's not a big deal. Good. So any of those resonance forms is a reasonable structure to show. The important one is this guy. Because what's better at bearing a negative charge, an oxygen or a carbon? Oxygen. So if we can show that that negative is being delocalized across some oxygens instead of carbons, we can predict that that's going to be a more stable intermediate. Are we all good with that?
If they're asking us to determine which type of reaction this is, so nucleophilic aromatic substitution, we should be looking for addition occurring first and then elimination.
Yeah. If it's a nucleophilic aromatic, we expect it to add and then eliminate. If it's benzene, we expect it to eliminate then add. And in benzene, there's going to be no electron withdrawing groups on there. And let's talk about the relative rates of that stuff. So of these three, which do you expect to react the fastest in the mechanism we just talked about? And those are all nitro groups. My handwriting is probably not the best, but we're not electrophilic aromatic anymore. We're doing what we did before, so we have to forget all those things we know about electrophilic aromatic. All right, it's going via the nucleophilic aromatic. So we know the hydroxide is going to bump into the chlorine, and the chlorine is then going to leave. But what does the relationship with the nitros have to do? Not EAS. They're not directing effects. No directing effects here.
So would it just be like spheric invariance?
If we put our negative charge, we have our negative charge here. Does that negative ever end up on the meta positions? No. So if a nitro is meta, is that going to be okay? Is that going to work?
It's not going to be favorable.
It's not going to help. Yeah, it's not going to help this reaction. Because at no point, remember, this one was the important one. In order to get to this one, we had to show that the negative ended up either on the ortho or the para carbon. All right? If it doesn't show up on one of those relative to where the chlorine was, we're not going to get that delocalization into the nitro group. All right? So I'm thinking that even though this guy does have two nitro groups on it, is that going to assist that negative charge when that intermediate forms? No. So is that stuff going to react in the nucleophilic aromatic substitution? No. This one will likely either not react or be very slow. Now, if we have 1 versus 2, which one's going to be better at delocalizing? 1 nitro group or 2? 2, so this one will be faster. All right? The way the ACS will sometimes throw these at you guys, and they'll try and try to confuse you, is they'll do something like this. Let's make this a bromine. Which halogen will get replaced by hydroxide when we react this stuff? Or let's use the NH2 minus the amide ion. Why the chlorine? Excellent. So our product will be almost entirely with the nitrogen replacing the chlorine, not the bromine. Does everybody see why? So we need to have, in order for this one to work, we need this nitro group to be either ortho. It either needs to be here, or here to delocalize that negative charge. If we have it meta, no reaction or very slow. And let me put slow / none. All right. So relative to these two, the nitro groups are ortho-pair relative to the chlorine, but not relative to the bromine. So the bromine's not going to get replaced by our nucleophile. Is everybody good with that? Nitro is, I think, the most common literature example. I've seen before where people use a trifluoromethyl. On the exam, I believe ACS usually sticks with the nitro. Yeah, like if you look in the review book, and then if you look in most textbooks, nitro is the example, because that's the one that people have worked a lot with. So if for some reason it's something weird, go with your best judgment call there. Like if it's multiple electron withdrawing groups and one of the answers seems reasonable, then go with it. But if it's not a nitro, I'd be weary that something else might be happening. Good. Do we have any questions on this? Yes, no, maybe so? No? All right. All right. I think that was all the mechanism stuff that I wanted to emphasize. So just remember with the alcohol that you guys are probably going to see some dehydrations of alcohols. My suggestion would be do a few practice problems with that. The chapter that is covered in is chapter 9 and chapter 13. So review chapters 9 and 13 for alcohol chemistry. And then the electrophilic aromatic and the nucleophilic aromatic and benzyne were all covered in chapter 19. Good? All right, let's take a moment. Do we have any, what are we at? We started at 2:30. We are about halfway through. Do we have any requests? Do we want to do more synthesis? Do we want to talk more mechanisms? More synthesis? Okay. So let's do that. Let's jump back to this guy. Real quick, just a reminder, I posted this on the website, so ucfstudyunion.wordpress.com. If you guys go click on chemistry, find this review session, and then this is linked there. Good? All right. So we already did A and B. Letter C says make propyl butyl ether with butane as your only carbon source. So let's draw that. So we want to make, we're starting with butane, and we want to make propyl butyl ether. Good? Ethers are kind of finicky. They're good solvents, mostly because they're unreactive. They don't react with a lot of things. And really one of the few ways to make them is via the Williamson ether synthesis. And what that requires is taking some alkyl halide and reacting it with some alcohol. So we'll do Williamson ether synthesis. And this is, if you guys want to review, this is chapter 14 in your textbook. But this often uses an alkyl halide and then some sort of deprotonated alcohol, the alkoxide. So going off this, I'm thinking that I'm going to guess, let's start with this. Let's say we use this guy, and let's say we use that alkyl halide. And then this will do a normal substitution. The O- will bump into the bromine and kick that guy off. We'll make that stuff. And now our challenge is going to be making that alcohol and that alkyl halide. So let's start with the alkyl halide, because that seems rather easy. Same as before, if we want to introduce functionality, what do we use? Bromine and light, or MBS and heat. And we get this stuff. Cool? Now we want to make that bromine on the less substituted position, so I'm thinking that our best bet's probably going to be to eliminate and then add. So I'm thinking we're going to use a bulky base here and eliminate. And then if we want to put the bromine on the less substituted position, what do we use? Excellent. HBr, and we want to use some sort of peroxide. That is one possibility. You could also use really anything with that structure. All right. For peroxides, let's take a moment to talk about these. Again, the ACS is not going to say R2O2 or ROR, like I know some of you are very fond of. They're not going to do that, so you actually have to know what a peroxide is. You're going to have one common one is benzoyl peroxide. That's where we have these two benzyl groups connected to one another. Another common one is where these guys are just alkyl groups, but just be aware that those are some examples of peroxides. All right, either hydrogen peroxide, benzoyl peroxide, these could be alkyl groups. All right, but some sort of peroxide is necessary to get this stuff going. Good? All right, so we have our alkyl halide. Now we want to make our, this guy. These guys can be made a number of ways. One possibility is to take the alcohol of choice, and you can either use some sort of metal, so sodium, potassium, magnesium, and you can do what's called a dissolving metal. So what that'll do is it'll insert the metal in there, it'll form hydrogen gas, and you'll get fairly pure of whatever alkoxide you want. The other way to do that is to react this stuff with sodium hydride, and you'll also get the base that you want. Good? But if you take some pure metal, so any one of these guys, sodium, potassium, magnesium, I think the common one actually is lithium. I think that's usually what people use, and you'll make the O-. Good? But now we want to make this alcohol. What is a common starting material for alcohols, or what's a possible starting material? Well, yes and no. Remember, we want to make it from butane. So let's talk about that guy. Could we get rid of a carbon here? Yeah. So I'm thinking we could have used this stuff as our starting material, and that stuff can very easily come from that stuff which we already made. Good? How do we reduce the aldehyde into the alcohol? What does LAH stand for? Again, general rule of thumb, don't want to use, and actually we don't even have to do this step. If we use lithium aluminum hydride, what we'll get is O-. We don't even have to do this path because we can just use lithium aluminum hydride. Don't follow up with acid. All right, if we follow up with acid, we will, we'll make an alcohol, and then we have to do a whole other step. But if you just use this stuff, you'll get that alkoxide. Good? If I want to get rid of that carbon, I want to cleave that carbon off to make an aldehyde, what do I use? Excellent. So start with O3, and then you can either use that dimethyl sulfide, or you can use zinc and H3O+. Good? And if I remember correctly, the ACS does like that one quite a bit. I think that one shows up in that review book a few times, and then the last time I took the test, I think that was the one that was used. Good?
How does that mechanism work?
I don't know. Yeah, I imagine it's, well, I could take some guesses at it, but I don't actually know. Yeah, it's going to deliver electrons, because that ozone, what it does is it like grabs onto the double bond and makes like this weird 5-membered ring, and then that like breaks apart and forms like this odd-looking double-barreled aldehyde thing, and then there's like an electron source, but how it, like the exact mechanism, I don't know. All right, do we have any questions on this? Any questions on any of this we talked about? Williamson ether synthesis, functionality. We already talked about differing bases. If we wanted that middle guy, we could have used sodium methoxide or potassium hydroxide or something like that. Cool? All right, let's do another one. So we want to make 1,3-cyclohexadiene from cyclohexane. So we have cyclohexane, and we want to make 1,3-cyclohexadiene. Good? I'm thinking the best way to go about that, well, what do we have to do first? Yeah, we have to introduce some sort of functionality. No, you can do either or. HV. It's not a big deal. Yeah, MBS can also be done with HV. Yeah, when I took the exit exam for the chem program, I got really confused because they used light instead of heat, and I had to like take a minute. I'm like, wait a minute, it's just a radical initiator. So it doesn't matter. It's just something to initiate radical formation. It depends on what exact radical you're using. So like if it's a very high energy cleavage, then light or a peroxide usually works better. If it's something like low energy, then you can like just boil it up a little bit. But if you're trying to get like for instance, if you're trying to get chlorine to homolytically cleave, that's really high energy. And using heat requires a lot of heat. Whereas with light, if you use the right wavelength, it doesn't require you to heat that up as much. So it depends on how you want that stuff to cleave. From here, what do we think we should do next? Yeah, I'd go with elimination. Doesn't matter what base, so we could use that, or we could use that. We could use this stuff. All right, we have any variety of bases will work here because there is no more or less substituted. What's the next possibility? There are two paths here. Do we know a way to add bromine selectively to a alkene? Yes, so we can either add Br2 and we can add across the double bond. Or what if I used NBS and heat here? What would happen then?
Form one away.
Yeah, it would make the allylic. Yeah. And in either case, you can use strong base again, and both will give you the desired product. All right. Either one is doable. Good? Any questions on that? That is one possibility, but it can also add allylic, and it can add benzylic, or if you have an alkane, it can add to the most substituted position on the alkane. All right, yeah. N-bromosuccinimide is useful synthetically because you can add bromine selectively to a variety of positions. All right. Does everybody see the difference in those two pathways there? So in the top one, the bromine is adding across that guy. Note that that mechanism is kind of interesting. So if we have a double bond and we react it with bromine, the first thing that happens is that guy grabs the bromine, kicks the other bromine off, and we get this brominium ion. From here, that bromide will then attack and kick that off. And what we get is a trans relationship between the bromines. Good? Now, bromine does not have to be the nucleophile. If you dissolve that stuff in a very dilute bromine water solution, what you can do is you can preferentially add water instead of the bromine in the second step. All right, so does everybody remember that halohydrin formation? If you take if you take this guy and treat it with Br2, it'll hit there, and you'll get that brominium ion. And then from there, you can use a variety of nucleophiles to attack. Whoops, bromine there, and nucleophile there. And that nucleophile could be water, it could be methanol, it could be ammonia, it could be methylamine. It could be dimethylamine. All right, all of those could be used in place of the nucleophile, and you'll have a bromine and nucleophile. Again, they're in a trans relationship to one another. Good? Any questions on that? Yes, no, maybe so? Yes.
If it's like not symmetrical like that, would it go to more substituted, less substituted?
The nucleophile will go to the more substituted. Yeah, so for instance, if we took this stuff and reacted it with Br2 and ammonia, we would get that stuff, hypothetically. The nucleophile will go to the more substituted position, generally. Because what happens there is that brominium ion will kind of start to break apart. So for instance, if there's a tertiary carbon, it will start to leave. Because that three-membered ring is very strained. And then if you remember, bromine's kind of big. So that thing's really hard to keep together. So it'll open up a little bit, making like a tertiary carbon fairly electrophilic. So the nucleophile will be more likely to attack the tertiary carbon versus the other one. Good? All right. So what do we have? We have some options. Does anybody have any synthesis requests, so any particular categories that we want to go over? Yes, no, maybe so. We're good. All right, we'll keep going on the list. So the next one says to make cyclopentanone from cyclopentane. So we have that stuff, and we want to make this stuff. There's a variety of pathways, some better than others. The very first step is going to be the same as always. We're going to introduce some sort of functionality. Yeah, if you're starting with an alkane, you usually want to introduce something that you can then work with. Bromine's the easiest one to add. Yes. But it's just, huh?
I don't know if can I say a thing one thing?
Yeah.
I would do them like maybe use the term wait. No, I lied.
Okay.
Couldn't you just eliminate that water pressure bond and
Yep. That is one step we can eliminate. Use aqueous acid to make this an alcohol, and then we can oxidize to make the desired end product. Yes, you can use a pyridium chlorochromate. You can also use sodium dichromate. You could also use potassium permanganate. All right. Just a general rule of thumb: if you guys see hypothetically, yes, but you're probably going to get some elimination product in there. Yes, you could probably go to that stuff by boiling that up in water. Maybe adding a little bit of sodium hydroxide. But ideally, the elimination and then the addition of acid is probably better. Sodium dichromate, the potassium permanganate, and then the yes, potassium permanganate. These guys are all oxidizing reagents. All right, they'll come with a variety of other stuff, so either acidic or basic conditions, so H0 plus, NaOH, water. But just if you see those two, oxidation is very likely going to occur, or cleavage. Those guys will very often cleave things and break them apart. Yes.
When can it cleave and not cleave? Like, can it be tertiary? Can it be primary, secondary? When do you decide?
When does it work?
Okay.
What do you mean?
Because like I remember there was one question in class where we were doing a reaction and we couldn't have used sodium dichromate to cleave whatever it was, like whatever category a molecule it was, because it was like tertiary and you couldn't cleave it or something?
Well, with tertiary alcohols, you can't oxidize them at all
Okay, so
because there's no hydrogen. Because the way these things work is that you have a hydrogen here, and you have a hydrogen here, and your oxidizing reagent, and this is not a mechanism, but just kind of a thought, is that it grabs those two hydrogens to form a double bond. And so you get your oxidizing agent will typically leave with those two hydrogens. How that happens depends on the oxidizing agent, but just, it
Same
depends.
thing for
but it needs an available hydrogen.
Yeah, it needs a hydrogen on both the alcohol and on the carbon below it. So we can oxidize primary, we can oxidize secondary, and then, but the mechanisms, all those we don't have to know. We just have to know that it'll form a double bond. Good? Any questions on this? No? All right.
Are those the only functionalities of potassium permanganate?
Say that again.
Are those the only like, things it does? Like potassium permanganate oxidizes?
No, remember if we have a,
I use that all the time.
if we have an alkene, we can use potassium permanganate, sodium hydroxide, and under cold conditions, we can make the diol. Now, if you heat that up, if you like continue to heat that stuff up, it'll end up cleaving and making, I think it's carboxylic acids. I should probably look that up to be sure. But I think when you heat that up, it cleaves that further. It like cuts that guy down the middle. Let's put a question mark there because I don't actually know that for sure. But when you heat that up, it continues on to do. My best guess would be that it cleaves into carboxylic acids. But this was the one that they taught you in chapter 9. And then some universities, we don't do it here, but I know some universities go into the details of like potassium permanganate with basic and cold, potassium permanganate and neutral, potassium permanganate and acid, and then the difference is heat and cold make, and it's a whole hot mess. Just know that it oxidizes. So whatever you're doing, one of the answers should be reasonable. There may be two reasonable answers, and just go with the one that seems the most logical. But like if you heat that stuff up, I think it forms carboxylic acids. And again, I don't know that for sure.
Looks familiar.
Yeah, it sounds reasonable, but it could be wrong. There are a lot of things that sound reasonable that could be wrong. Cool? All right. Next. All right, so let me present some options to you guys. We can either talk about alkynes, we can talk about alkenes, we can do alcohols, or we can do elimination and substitution. Do we have a preference? We can do alkynes. Does anybody else have a preference? Alkynes.
Do you have any acids and bases on there?
Like ranking acids and bases? We can do some of those. I don't have any on here, but we can do some. Yes, yeah, we can rank. We'll talk about acid base. So we're gonna do alkynes, acid base, and do we have any other requests? No? All right, so let's do alkynes and then we'll do acid base stuff. All right. For alkynes, let's start with this guy. An organic one, this is usually everybody's least favorite stuff. It's ethine or acetylene, depending on who you ask. You can do a lot of cool chemistry with this stuff. One of the first things that you can do is deprotonate this stuff. What sort of base do I need to use to deprotonate that guy? Yes, sodium amide. We use a really strong base here, right? Hydroxide will not work. The relative pKa's are too far apart. Like water has a pK of like 16-ish, I think it is, whereas the alkyne has a pKa of 25, but then ammonia, to get it to the amide ion, that pK is like 36. So those are far enough apart to where we can use this stuff to deprotonate, so it'll grab that proton, leave behind a negative charge. So we'll get ammonia as one of our products, and then the other product will be negative this guy with the sodium counterion. Good? Now this stuff can act as a nucleophile. All right. Typically we prefer primary alkyl halides with this. Secondary will work. It'll work. It won't work very good, but it will work. Tertiary is hopeless, okay? If the ACS asks you a question and they say you reacted with some tertiary alkyl halide, Mark it wrong, all right? That's not going to be the correct answer. Are we all good with that? All right, this stuff is a strong nucleophile. It's preferentially going to go SN2, yes?
Is there any way to know, like, what a react with tertiary? Just 'cause it's strong? That's it?
Yeah, generally strong nucleophiles will not react with tertiary alkyl halides in substitution. They will react with it, but it will do an elimination. Yeah, if you guys had someone good or me for organic 1, you would know that, but I didn't see a lot of you for organic 1. All right, so this guy will attack in here, and it'll knock that guy off. And what we'll get is 1, 2, 3 connected to the carbon, connected to that guy. Good. Counter carbons. All right. I think there's very frequently times where the ACS will show you. Yeah, it'll look similar, but when I took organic 1, the person I took it with would often get really mad at the class when they would mark answers like that, and they'd be like, where did carbon come from? Cannot pull carbon out of pocket. So it's very true. You can't pull carbon out of your pocket. All right, there are 2 here, there are 3 here, 3, 2. All right, you can't magically make 1 more carbon appear. Are we all good with that? Yes, nobody's going to tell someone otherwise. All right, carbon doesn't just magically appear. That'd be nice, but it doesn't happen. We can repeat this process if necessary. So we can treat it once with that sodium amide and then follow up with some sort of alkyl halide. And what we can get is, we can add that alkyl halide. And again, this preferentially should be primary. And then secondary is okay. Tertiary is bad. No tertiary. Are we all good with that? Yes? All right, let's jump. Let's do this. So let's work with start with this stuff. So I'm just going to say we have that. We have a variety of things we can do to alkynes. A lot of the reactions that we can do with alkynes, we also learn with alkenes. One is the addition of HBr. The exact same thing is true when we did when we did alkenes, is that if we add the HBr across there, it'll go more substituted. I've been asked this before, and I'll answer it because I hope someone would think about this, but I don't know if you can use peroxides here. People have asked that before, and the answer is I don't know. My guess would be probably, but I've never seen that, so I don't know if that's a thing. But hypothetically, a peroxide might work the same way that it does with an alkene, but again, I don't actually know if that's true or not. One of the limitations to this reaction is that, think about the intermediate here. When this guy reacts with another equivalent of HBr versus this guy, which one of these is more stable? This carbocation or this one? The second one, right? Not only is it an sp3 hybridized carbon, which is better than sp2, but then that bromine can donate electron density in. So which one of these do you think is more reactive? Which one's more likely to form? This guy, the first one, or the second one? The second one. Huh? This is a more stable carbocation. It's kind of like climbing a mountain, all right? If you're trying to get over that energy barrier, and the energy barrier is fairly low, then you can do it quickly and easily. So like, I'm thinking about climbing a hill versus climbing Mount Everest. All right, if you're trying to climb Mount Everest, it's going to require a lot of time and energy. If you're just a little tiny hill, it's not going to be that bad. This is the little tiny hill. This is Mount Everest. All right, that thing, there's a large energy barrier to get to that guy. So it's going to be very slow to form. But once it's formed and that's reacted, this guy is even more reactive. So it's really hard. It's really hard to isolate just the one addition of bromine. All right, that's not synthetically practical. All right, Oftentimes when you use HBr, you use excess hydrobromic acid and you get the double alkyl halide. Is everybody good with that?
This one, they're both sp2, right? So it just goes by the delocalization of phosphate bromine.
No, that's
What was it? Inductive, whatever
this. Yeah, that lone pair can go down. This is SP, and that's not actually a good drawing. That's SP hybridized. This is SP2 hybridized carbocation. This one is more stable than that one.
There's no hydrogen bonds.
Yeah, there's no hydrogen here.
So if you have an energy diagram, like how are those two different?
This one would be higher than this one, and the activation barrier to get to this one would be higher than the one to get to this guy. So and now this is not going to be to scale, but I would predict that it would be like really high and then down to product. And this one would be a little bit lower. Again, those aren't to scale, but that first one, this would be a very high. This first step here, that is a high activation barrier. It's a fairly high carbocation, so this is going to be a hard step to get to. Hmm?
That's for SP1.
Yeah, this is for this step, and that's for this step.
How do you know it's
The addition of HBr to a double bond or a triple bond, I think, is almost always exothermic. I would
I would say triple bond is more stable. Like destroying it would be endo, you know?
No, we know how to rank alkenes based on substitution, but ranking alkyl halides versus alkynes or alkenes, I think those are usually exothermic reactions. Good. Any questions on this?
Alkenes go through endothermic, right, usually. What's an alkene?
Those are exothermic. The addition, absorbing energy.
So what's an example of a compound that forms a double bond? Would that be endothermic?
Yeah, I think the elimination from an alkyl halide to an alkene, those are endothermic. Generally speaking, the majority of the reactions we talk about are exothermic just because endothermic reactions, while possible, are usually harder to do. It's harder to get that equilibrium to shift that way. It depends on other factors. All right, let's talk a little bit more about triple bonds. Let's still use this stuff. Let's say I want to make this stuff into a ketone versus an aldehyde. What will be the difference in the reagents here? If I want to make it into the ketone, what should I use? Anybody remember? Nothing? Huh?
Not sodium tetrahydride?
No, we're adding, well, in both these cases, the intermediate is going to be an enol of sorts. It'll either be the primary enol or, we don't know what's on the other side, but it'll be the enol. How do we add water to a double bond? H3O plus. So in this case, we're actually going to use H3O plus and some source of mercury. No. The reagents that are commonly used for this are mercury sulfate, sulfuric acid, and water. The mercury is necessary. If you just treat a triple bond with aqueous acid, it will react eventually, but you have to really boil it up and you have to wait quite a while. Right? The mercury is necessary to help stabilize the intermediate. Cool. We already talked about this one a bit before. If I want to make the aldehyde, what do I use? Yes, it's going to be the bulky borating agent, followed by sodium hydroxide, hydrogen peroxide, can't use another peroxide here, and water. Whoops, my bad. R2BH, no 4. Good catch. And then let's, where did that go? What the heck happened? Not that. Oh, here. And then remember we talked about this a little bit ago, that R2BH can be a number of things. All right, that I think is 9-BBN. There can also be cyclohexyl rings there. There could be terbutyl groups there. It can be any bulky alkyl group. So just on the exam, if you see a bulky alkyl group in your head, think R2BH. All right, and then the follow-up step will still be the peroxide and hydroxide. Good. All right. Any questions on that? No? And remember, both of these will go through that enol intermediate, which will spontaneously tautomerize into the keto form. Good? Yes? All right. What else do we got? Some other reagents with, we want to do acid bases. All right, let's do acid bases, and then let's jump back and talk about epoxides, because those are one that people tend to be kind of rough on, just because I think we miss them in organic 1 since it happens right at the end. What do we? Okay, we have about 35 minutes left. So let's talk about acids. So we're going to compare first some of the 3 listed. We have a phenol, a carboxylic acid, and we have an alcohol. Which one of these is the strongest acid? Yeah, carboxylic acid is strongest. Then which one? The phenol, and then lastly the alcohol. All right. There are a number of reasons for this. The carboxylic acid, when that thing gets deprotonated, that negative is delocalized across 2 oxygens. It's a very stable ion. When the phenol gets deprotonated, that phenoxide, that charge is delocalized across multiple carbons, which isn't as good as 2 oxygens, but it still helps beef that up. The phenol has a pK of about 10-ish. A carboxylic acid's around 3-ish, and then alcohols are about 15-ish. All right. So just note that difference here. You guys don't have to have pK values memorized, but you do have to know the difference between these 3 groups. All right. Carboxylic acids are more acidic than phenol, are more acidic than alcohols. All right. The next factor to consider, if you have a series of either one of these, so let's say we have 3 different phenols, and we want to talk about the acidity of those phenol molecules, what sort of R group will make that thing more acidic? Remember that the conjugate base of any one of these acids, so let's say we'll use phenol as our example, the conjugate base is going to be a negative. All right? Remember that to stabilize a negative, we want an electron withdrawing group here as our R group. All right, we want something that's going to pull electrons away from that negative charge. Does that make sense? So if I want phenol to be a stronger acid, I want to put an R group on there that's going to delocalize the electron density. So a nitro group, a trifluoromethyl group, an aldehyde or a ketone, anything that's going to pull electron density. If you want to weaken that acid, what you can do is put electron donating groups on. So like for instance, if we were to compare phenol versus say an anazole group, which one of these would be the strongest acid? Excellent. This guy would be strongest. Which one would be weakest? Yeah, because this guy's electron withdrawing, this guy's electron donating, so this would be weakest, and this would be number 2. Good?
So you want the like, okay, when you say like it's donating or whatever withdrawing, you want it to be less negative to oxygen of the alcohol?
Well, you want its conjugate base to be less negative. You want something that's going to delocalize, because remember, nature doesn't like charge buildup. It wants to delocalize negative and positive as much as possible. In this case, we have a negative, so we want something that's going to absorb that electron density as much as possible, to delocalize it. Good? And that story is true if that is an alcohol, if that is a phenol derivative, if that's a carboxylic acid, right? All across the board, the electron withdrawing group is going to make that a stronger acid, all right? And we will also want to know this relative ranking. I think oftentimes people forget this, and then what the ACS will do is that it will throw a bunch of these in there. This is a starting point. Rank them based off the functional group, whether it's an alcohol, carboxylic acid, or a phenol, and then consider the electron withdrawing effects. Are we all good with that?
So an electron would actually be more than the alcohol because there's no conjugation.
Well, this has no conjugation in the conjugate base. This has 2 oxygens. This has 1 oxygen and 1, 2, 3 carbons. So even though there's more resonance forms than this guy, the 2 oxygens beat out the multiple carbons.
There's no more resonance in that carboxylic acid because of the carbonyl group.
This guy, if you draw resonance forms for this, you can draw this lone pair coming down. There'd be 1, 2, 3. So you'd have 4 resonance forms. There's only 2 for that guy.
It'll just be over the carbonyl.
Say that again?
Just be over around the carbonyl.
Yeah, there wouldn't be any delocalization to the ring. But the 2 oxygens better than the multiple carbons. Good? Don't overthink this. Don't try to memorize a bunch of rules. Just, we want the thing that has the most stable conjugate base. That's going to be the strongest acid. All right? And then I always have people tell me where they're like, oh, like the most stable acid or something, and then it means the weakest base or the strongest acid and the strongest base. I find that confusing, and I find that people usually confuse themselves by doing that, so try to avoid that. Think one at a time. If we're talking about an acid, we want the more stable conjugate base. We want something that's going to withdraw electrons, right? Go through that logic every time. Don't try to correlate acid strength and base strength. They don't always match up the way you think they would, all right? Don't do that. Do acid strength first, and we'll talk about bases here in a minute. But is everybody good with this? They could do this if we're on the ACS exam. You'll probably get a question or 2. It's very likely. Yes? All right. Let's talk about bases. All right. Now, it's tempting to try and lump those 2 together. Don't do it. All right. Think about them separately. If I have some base by the Lewis definition, by Lewis acid-base theory, what does a base need to have? Yeah. By Lewis theory, it needs to have electrons. And it donates those guys. Good? So our base should have some sort of lone pair on it, ideally. So let's use nitrogen. Let's actually use aniline as the example. Aniline has a lone pair on it. It's a decent base. Not a very good base, but it's decent. If I have a group here, and I want these electrons to be more available to act as a base, what should that R group be doing? Donating. So to make a stronger base, we want an electron donating group, and that'll make a stronger base. Good? Yeah? If we compare aniline, and we're actually going to do a series of these. Which one of these is the weakest base? Yeah, it's going to be parole. And that's spelled like that, not like the thing you don't want to do. I mean, number 3, this is the weakest. That's because it's aromatic. The lone pair is participating in aromaticity there. Yeah. Yeah, completely delocalized. That lone pair is completely smeared out across that ring. Aniline just has conjugation. So anilin's still delocalized, but it's a conjugated lone pair, not aromatic. Right? The ring is aromatic. The benzene ring is aromatic, but the nitrogen of aniline is not participating in aromaticity. All right. And last but not least, this alkylamine. This guy, yeah, they're very localized. There's no delocalizing effects. So this guy is number 1. It's the strongest. Yeah. So we could rank based off this, whether it's an alkylamine, whether it's got a whether it's conjugated, and then if the nitrogen's involved in aromaticity. And then from there, we can rank it based off electron withdrawing or donating. Right? And remember, an electron donating group is going to beef up that base strength. An electron withdrawing group is going to crap up the base strength. Yes.
If there was an electron donating group on the aniline,
Yes.
would it be better or still weaker than the second one?
You mean if we put an electron donating group here compared to that?
Yeah.
The electron donating group doesn't have that large of an effect. I'm sure there are some derivatives where if you put enough electron donating groups on, it could beef it up to be sort of like this, but these guys are magnitudes apart. Like this conjugate acid has a pK of like 4, this conjugate acid has a pK of 9. That's an order of 10 to the 5th difference. So what is it, like 10,000 or 100,000 times? 1, 2, 3, 4. Yeah, that's 100,000 times different. The substituents on that guy are not going to help that much. Good?
So for the aniline, the electron dominant nitrogen are being used in the aromatic. Like, can be useful for numbers like figure this out.
No. They're not involved in aromaticity. They're just delocalized via conjugation. Good? All right. This same story is true if we use any sort of negative charge thing or something with electrons. So for instance, if I had a series of sodium salts with oxygen, no, let's not do that. The same story is true. This guy is a stronger base than this guy, just like how that stuff was stronger than that stuff. Good? And we could actually even throw the oxygen equivalent in here. All right. That stuff is a terrible, terrible base. Everybody good with that? Yes? Ranking wise, the negative, so let's take HO minus yeah. If we want to rank those 3 by base strength, which one of those is the strongest base? Yeah, so well, let's start with atom. Which one is going to be the stronger base, the nitrogen or the oxygen compound? Let's ignore those two. Which one's stronger, nitrogen or oxygen? Less electronegative is stronger base, the nitrogen. And then which one is stronger if we compare neutral versus negative? Negative. So I'm thinking that those two are going to be the strongest. And then between those two, the nitrogen's the stronger base, followed by the hydroxide. And then, now these guys, which one is stronger, ammonia or water? Ammonia. And water's...
Would it be like the N negative and NH3?
No,
Why? Why is OH minus better than NH3?
because it's a full-blown negative. Yeah.
But negatives are good.
Yeah, so we could rank these as saying H2N minus is stronger than hydroxide, is stronger than ammonia, is stronger than water. And then note that these could have, instead of hydrogens, these could have R groups on them, okay? That trend will remain the same based on if they're R groups or not. Are we all good with that? Yes. What I would suggest doing is, if you're not really good at understanding, I would memorize this order, just because that in those hydrogens, and then also know that those hydrogens could be R groups. But that order should remain the same, as long as those are alkyl groups and not like something weird or interesting. Good? Yes? Any questions on that? Does that work for acid-base stuff? Yes? All right. Let's talk about epoxides real quick, because those show up, and I think oftentimes we forget those in organic 1, and epoxides are actually really useful synthetically, and they're also really interesting. Oh, let me sit down real quick.
What's that one that they do MCBA and H3O plus? What do they do then?
That makes a diol.
What, diol?
Yeah. Okay. So let's start about epoxide synthesis. So if you start with an alkene, you can make an epoxide by using some sort of peroxy acid. Note that a peroxy acid has the structure of that, and that R group can be just like the peroxides. The peroxy acid can have a variety of R groups. That could be a methyl, that could be some sort of alkyl group, that could be a benzene ring. The one that we learn about in organic 1, and it's actually the one that's most commonly used, is that, what am I doing there? O, and that should be an H. My bad, I can't draw. Is that metachloroperoxybenzoic acid, MCPBA. Good? All right. When we do that, what we end up getting is an epoxide. And then we can react epoxides with a number of things. One possibility is reacting it with water, or H3O plus. When we react that guy with acid, what we end up getting is a trans diol plus the enantiomer. Good? We could also react that stuff with some sort of base. So we could react that with a nucleophile. All right, the nucleophile will react in, and a similar story. And we would do that in one step, and then the second step we'd use acid. But what we would get is a trans, we get that nucleophile and that OH. And remember, nucleophiles can be a number of things. It could be cyanide. It could be some sort of alkoxide base. It could be a Grignard. Right? All of those are reasonable nucleophiles to use with the epoxide. And now what we have is a variety of ways to make that into something interesting. So we can add the cyano group, and then remember we can react cyano groups with Grignard. We can react them with acid and heat to produce carboxylic acids. We have a large variety of things we can do with those. We can make that ether using the alkoxide, and we can just add a boring old R group by using the Grignard. Everybody good with that? Well, it has to go trans. Yeah, when the nucleophiles attack, it has to go trans, because when it bumps up underneath, it knocks that oxygen off. And it has, these have to add trans. Good?
So it's a methyl on there, would the nucleophile add like more substituted, or would that just
We'll get there. It depends on the conditions. So someone just asked about, well, let's say we had this stuff. Let's say we made this stuff into an epoxide. And there should be a double bond there. And the question becomes, well, where does it add? Remember when we talked about SN1, SN2, and all that junk? If we use a strong nucleophile with a good leaving group, it preferentially goes SN2. And where does that guy preferentially attack? The less sterically hindered, so the less substituted. So the nucleophile is going to add here if it undergoes, yes, if it goes undergoes SN2. When we do SN2, what's favored? Primary, secondary, or tertiary? Primary. So it'll preferentially go primary, then secondary, and then tertiary under basic conditions. So if you have one of these guys or hydroxide, those are basic conditions, and it will preferentially go primary, secondary, then tertiary. Now, there is an exception to that, and that has to do with acid catalyzed conditions. I'm going to tell the quick version of this story. If you guys want, if we want to talk more about this, we can. But if you guys use H2SO4, and let's say we use methanol as our alcohol, the first thing that happens is that this guy will get protonated, and what you'll get is this OH plus with a methyl. That guy, the argument that's used is that that guy has, and I'm hesitant to say resonance form, but I guess that's the best one to use, is that that guy really has that oxygen leaning out quite a bit, and that bond, that bond is strained, and this carbon, this tertiary carbon, is a lot more electrophilic than one would expect. And so our methanol will preferentially attack that guy and there will be a loss, there'll be a minus a proton here. And then remember that this stuff will be such that the oxygen will be up and the methanol would be down. All right, so this would be trans. Huh? It is, well, it's an okay nucleophile. Methanol is not like methanol. No, the acid conditions, why does it go more substituted? If you just use methanol, it would likely go normal substitution and go less substituted. Yeah, and now note this trend is weird. It's tertiary, primary, then secondary. All right, the tertiary is the only one that's the oddball here, okay? So for epoxides under acidic conditions, tertiary is preferentially attacked, then primary, then secondary.
So if you had like a primary and a secondary there.
Primary, even, yeah. Because if you think about that, the only carbocation that really is like reasonable to form is a tertiary carbocation. Secondary is still pretty high in energy, so that thing opening up to form a secondary pseudocarbocation isn't as favorable as the sterics there. Good? Huh?
I used to know this. Like, there's just so much to know. I just don't know what to like. I don't know. There's just so much to know.
I'm just gonna accept it. Like, I'm just knowing basic trends and basic stuff that's worked for me.
Yeah, just, I mean,
There's no way to know everything. There's literally no way.
the test isn't designed to get 100 on.
Yeah, I know, like, that's hard.
Yeah, I know that's probably not heartening news, but yeah, the test isn't designed to get 100 on. It's supposed to separate people out and show trends. All right, before I forget, let's talk about, we have about 13 minutes left. Let's talk about carbines, just because this is not covered in Organic 1 or 2, but it does show up on the ACS, and this way you guys will know.
Wait, this is the CH2 active.
Yeah, So
Why do they test on this not what legit? So like if it's not synthetic. Is it in the book?
no. Oh wait. These are just two reactions. The mechanisms aren't very important. Well, they are. They're interesting. The mechanisms are very interesting, but you don't have to know them. What you do have to know is what they form. And I'm not going to draw wedge or dash here. This is interesting to think about. If I have 3 points, if I have a triangle, is it possible to like have 2 points locked in place and then have one thing go down and one thing go up and still form a triangle? So can you have a trans epoxide or cyclopropane? Does that make sense to everybody? Like you can't, that's not possible. It has to be cis. If you can show how that's possible, then you're going to be like a geometry, you'll go down in history. But there are two reactions we want to know. The first one is called the Simmons-Smith reaction. It uses diiodomethane and zinc, and it turns an alkene into a cyclopropane. All right. From here, there's not a lot that we can do. It just, this is how cyclopropane rings are made synthetically. The other reaction that can be done, is to make a double-barreled chlorine-looking thing. It still forms that three-membered ring. The reagents of choice, though, are is chloroform and tert butoxide. All right, so a base and then that chloroform. All right. Again, the mechanism usually isn't tested, but you should at least know those reagents. So if they show up on the exam, you can predict the product. Are we all good with that? Yes. The other one that I've seen done, and I don't think this is really a good reaction, but no, this is not something you guys should have seen before. This stuff, I mean, that is Wittig, but this is an organometallic reaction. Yeah, this is a weird one. This showed up last year. I didn't know that people taught this on Organic 1, but let me make that a little clearer so it's easier to see. It's a palladium catalyst with 4 triphenylphosphine groups attached to it. And what that will do is that will couple sp2 hybridized carbons with an alkyl halide and will replace the alkyl halide. All right?
So we're competing against like the smartest of people, right?
I really hope the national average is really low. I just hope everyone in the US is dumb, so that way
Well,
ACS over
that's
here will be bad for us.
that's a reasonable hope. But yeah, just again, that's another reaction that they don't show you in Organic 1 or Organic 2, but I have seen it show up on the ACS before, are these 3.
So it just replaces the bromine, that's it?
Yeah, it's weird. There's a variety of these that can happen. The most common one is with a palladium. This is called the, I think that's the Nageshi or the Heck. I don't remember which one it's called, but it will couple those two things together. The mechanism's weird. It has some inorganic chemistry in it, but you might want to know those reactions. They may show up. They may not, but I have seen them in the past. Are we all good with that? Yes? We still have about 9 minutes left. Do we have any other questions? Anything we want to talk about last minute? We're good. These are carbenes. So they form they're interesting because they form this, this carbon that has both a negative and a positive, and so the result is a net neutral species, but they're very reactive. Those are carbenes. Yeah. You don't have to know anything else. You just have to know the reactions. That way, if they show up, you can predict the product fairly easily. Good. Any other questions? We have a few minutes. Do we have any other topics that we'd like to do? Yes.
What's
Well, yes and no. The isoelectric point, the pi, is the pH at which a molecule is net neutral. Now, something like cyclohexane, its pi is all pHs because it can't be deprotonated.
Okay.
So cyclohexane, can you deprotonate that at a pH of 12?
I don't know.
Cyclohexane.
Yeah.
Let's go easy. Let's go methane.
Yeah.
Can you deprotonate methane at a low pH?
No?
CH4. Can you deprotonate it at all?
I don't know why, like, because it's a base? Is that, like, no.
CH4, methane.
Yeah.
Can you deprotonate a carbon? Can you just dump some base and yank a proton off?
No.
No pH can you do that.
Why? Just explain. Just dumb it down a bunch.
My response is retake Gen Chem.
Great.
Yeah, that's the response. Can't deprotonate methane. So like the isoelectric point of that guy would be all pHs. There is no pH at which it's on a charge. Amino acids, however, can be deprotonated at multiple points.
Okay.
And so its isoelectric point is the pH at which it has a net neutral charge. Now Zwitter ions, those are things that have both a positive and a negative. So like let's talk about glutamic acid. Let's compare butanoic acid versus glycine. And this is at low pH. Cool? If we move up to, say, pH of about 7, what we get is butanoate and the deprotonated form of cool. So at low pH, that is net positive and that's net neutral. So the hypothetical isoelectric point of butanoic acid would be a low pH because once you take it up to neutral conditions, it's going to be mostly deprotonated. So it will have a charge. But this has a charge at low pH, so this is not at its isoelectric point. But when you move it up to a pH of 7, the carboxylic acid gets deprotonated, the amine stays protonated and positive. A Zwitter ion is something that is both negative and positive, and it just so happens that when this guy is a Zwitter ion, it is at its isoelectric point. Up here, these guys are both deprotonated and negative. They are not at their isoelectric point. Cool? And for anyone who's like a history buff, or a language buff, I guess I should say, Zwitter ion, it's German for hermaphroditic ion, but it means it has both parts. So it's both a negative and a positive. Yes. Whoever came up with that was wonderful. Yes.
When you're using that HVZ, is it
H.
Hell
Volhard-Zelinsky?
Yeah.
Yes.
Is it NH2 or does it become NH2 plus? Because I know it's not an acid. Is it an acid?
It would depend on the conditions.
Because the other ones are always in like acid. There's always like H2 plus is the last second heat.
Well, now in that one you're reacting with excess ammonia, which is a base.
Yeah.
I would predict. Oh, thank you. It should be deprotonated.
So it's NH2. So that's
Yeah.
the only one that's generally NH2.
And the carboxylic acid should also be deprotonated because it's in base. If you mix ammonia
Yeah.
and acetic acid together, yeah. Which is why you need excess ammonia.
So deprotonates both.
Well, it'll deprotonate the carboxylic acid, and then the excess ammonia will react with the alkyl halide. Like, if we're talking about a sequence of events here, if you react this stuff with ammonia, the very first thing that happens is a deprotonation. So you need excess ammonia to be able to react with that. To be able to react with that guy. Because sequentially, this happens first. Deprotonation, acid-base chemistry happens instantly. a substitution requires time and energy and things. So you have to put
How
excess.
difficult does it make it just an OH? Like it ends as like OH.
Well, they're just wrong. That happens. It's okay. Yeah, you can't have an amino acid that has a neutral nitrogen and a neutral carboxylic acid. That's science fiction. That can't happen. They're like if you have 1 mole of an amino acid, maybe a couple hundred molecules will be totally neutral. But those are in such low quantity that we don't even consider them. Because remember, a mole is like 10 to the 23rd molecules. That's like millions and millions of things. Are we all good with this? Yes? We're out of time. Don't forget, there are other organic sessions. If you guys stop at the table down at the atrium on the first floor, they have a schedule. I have an Organic 1 review on Tuesday from 5 to 7. You guys are more than welcome to come hang out with me then. The only stipulation is that it has to be Organic 1 material because there will be Organic 1 students there. All right, so if you guys come in with Organic 2, I'm going to tell you no, the Organic 1 students have priority. But you're more than welcome to come to the Organic 1 review. All right? Have fun studying and enjoy the rest of your evening.